Hi, hello, welcome to Knowledge Center. In this video, let us understand the logical instructions used in microcontroller. You might have studied about logic gates. We have a basic logic gates like AND gate, OR gate and NOT gate. Then we have a special universal gates like NAND gate, XOR gate. Now in microcontroller 8051, we have all these three basic gates like AND, OR and NOT gate, and also we have an additional instruction that is XOR gate. Okay, so now generally we perform those logics using a gates, but in microcontroller by just writing one particular instruction we can perform the task. Okay, so let me write those instructions here and let me tell you what is the syntax of all these logical instructions first, and after that I will take one example to understand each instruction. We have AND logic. The very first logic is AND gate, and we represent it like A, N, N. AND logic, it stands for AN is AND, L for logic. AND logic, and it has to be followed with a destination, comma, source. This is the syntax of writing an AND logic instruction. Similarly, we have OR logic, and that has to be represented as ORL. We should not give any space between OR and L. It is ORL, destination, comma, source register. It may be a register or anything else. Next we have XORL. This performs according to the XOR gate logic. So XORL, destination, comma, source. And I told you about the NOT gate. The NOT gate is, the function of NOT gate is performed by this instruction. This is called complement. Complement destination. Okay, so we have four logical instructions, and these are those four logical instructions. I hope you have an idea about what these logical instructions or gates will do. I'll come to that point later. Before that, you understand here we have destination, comma, source in each these three cases, whereas here we have only one operand, that is destination. These things we call it as an mnemonics. ANL, ORL, XRL, CPL, all are mnemonics, and these are operands. We have two operands in these three cases, whereas here we have only one operand. Right. So, and one most important thing you need to understand in the logical gate, in the logical instruction, is all these logical instructions will not affect any flags in PSW. So whatever the flag we have in PSW, those flags will not be affected, like carry flag, auxiliary carry flag, okay, overflow flag. Those flags will not be affected using this logical gates. That is one important statement you need to make when you are explaining the things. Okay, and one more second important thing is, with destination, wherever we have a destination operand, this destination operand must be an accumulator. So in place of this destination operand, we have to put A. So it is mandate. Accumulator will act as a destination operand. Here also we can write, we have to use accumulator as a register. Whereas this source, it may be a register, or it may be a number, or it may be a, means you can use an immediate number over there, or you can just take a register over there. So there is an option here, but here we don't have an option. So this thing you need to understand before utilizing those instructions. I hope you got some idea about what is the syntax of it and how to write the syntax instruction. Now let us go in detail about individual instructions. So first let us come with an ANL. So AND logic, we all know that AND is going to perform in this fashion. Let me write the truth table of that. AND gate. It is going to have two inputs. One gate will have two inputs and one output. So the operation will be something like this. Both will be 0, 0, 1, 1, 0, 1, 1. If I give 0, 0, the output is going to be 0. 0 and 1, output will be 0, 0 and 1. This is what the truth table for AND gate. Means the output of a AND gate is going to be high only if both the inputs are high. That is what the general statement we know. Right. Now this concept can be executed using just one line, one instruction. So ANL, A, source. Now the question is, okay, how to utilize this? And the development or advancement what it is we have here is, generally we can operate this or we can execute this using an IC. But now no need to have that IC, no need to have that IC kit. We can just have an instruction and execute this task. Now let me tell you what is the application of AND logic, where you can use it and how we can use it. So for example, we know here that if I put a 0 at one input, the output is just following the other input. Look at this. If this is 0, output will follow the other input. Okay. And here the same thing. If any of the one input is 0, output is going to be 0. That's what the statement is. Now I am going to make use of this and let me tell you how we can apply it in our simple microcontroller concepts. So let me erase this. We generally use this AND logic for masking the numbers. For masking the numbers in the sense, for putting a mask on that particular number, particular bit. Okay? Mask is nothing but what? Covering. So we have to cover that number. For example, let me take one example. Like I have a number 38. So this is the number. So I will put it in a accumulator and I want to mask this 3. I just want to read 8. I don't want to have this 3 here. Means I have input as 38 but I want to read only 08. I want to mask this higher nibble. This is the lower nibble, this is the higher nibble. So I want to mask a higher nibble means I can make use of an AND logic for that. So simply I will tell you how to do that. So you can just whichever the number you want to mask, if you want to cover, you AND it with 0. Because we know that whenever we give input, one input as 0, the output will be 0. That's the point we know. Right? So what I do, this 38 first let me write it in binary. So this is 0011 and 1000. This is 38. Now I don't want to represent this. I want to represent this as 0 and I want this as it is. So here understand one simple logic here. If you want to have this output, this input as an output as it is, then you have to AND it with 1. So what I do, I put 1 in all these 4 bits and I put zeros here. So we are applying the AND logic. So understand, we are applying AND logic. 0 and 1 is 0. 0 and 1 is 0. 0 and 1 is 0. 1 and 1 is 1. That is what according to the truth table I am writing. And 1 and 0 is 0. This is 0, 0, 0. So what happened here? We had 3 and 8 and I am ANDing it with a 0 and F. In hexadecimal when I write it, this is 0, this is F. So when we AND the input with a 0 F, what happens? I wanted to mask this 3. So for this input, I have ANDed it 0. So whichever the bit you want to mask or whichever the bit you want to cover, you AND it with 0 for that particular bit. Okay? So when we AND it with 0, we got the result as 0. And here, if you want to display that result as it is, this input as it is, then AND it with 1. So all bits are high, so the output, you just look at this. Whatever the input I had, I got the same as an output here. So the result is 8. So now, the result will be 0, 8 and this result where it will be? It will be in accumulator. So whatever the function we do in these logical instructions, final the result will be in accumulator only. So once if I give the input as 38, after ANDing it with 0F, we get 08 in accumulator. So how to achieve this? By just writing this line, I will write the line here. A and L. Now this is what going to happen in AND logic. Now let us see how to write that in instruction. A and L, A, comma, hash, 0F, H. So A means, that is what I told you that destination has to be accumulator. So first give that input to accumulator. So before this I write like this, move A, comma, hash, 38H. So what I am doing here, I am giving the 38 as an input to accumulator and then I am ANDing that content of A with 0F. So how I decided this 0F? This is totally depends on our requirement. Now I want to mask 3 and keep 8 as it is. So in that lower nibble I will put F, in higher nibble I will put 0. So this higher nibble will be ANDed with 0, lower nibble will be ANDed with F. So we get the result as 08. So after execution of this line, accumulator will have 08 in it. Now you can cross check yourself by putting the question that if I want to mask 8 and I want 3 as it is. Okay. So after giving this 38, I want accumulator output as 30 now. So what input should I give here? You just think on it. It is just a fraction of minutes. You can think of it and you can get the answer. I want to cover the higher nipple. I want to mask the higher nipple and I want to keep this lower nipple as it is. So put 0 in this location where we have a lower nipple and we put F in higher nipple. Then we get the result as 3 0. So for that what you can do is 0 F 0. If you add it with 0 F 0, then we will cover that lower nipple, but higher nipple will be kept as it is, like this. Okay, and but this is 3 0. Actually I wanted 3. I wanted 3, but I have got 3 0. After masking I have got 3 0. So after this we have another special instruction, that is swap A. Use swap A. When we do this, it is going to interchange the nipples. Swap is nothing but what? It will just interchange the nipple within it. So interchange is nothing but now what happens after this? Accumulator will get 0 3. So this is how we can make use of an logical instruction, that is AND instruction. Okay, to mask the data, to mask the bit whichever you want. And it's not mandated that you have to mask only 4 bits and 2 bits. You can mask any number. You can mask any of the bits. Okay. Now I will give one question here, and you just work out and try to get the answer for that. I will have some input like, say for example, I want to mask 5th bit. I want to mask 5th bit of an input. 5th bit of an input. So whatever may be the input, I just want to mask or cover only the 5th bit. So what data should I enter here so that it will mask only the 5th bit of an input? We don't know what is having in accumulator. Say accumulator is having 38 only. So in that 38 I want to mask only the 5th bit. So you need to think about it, that what input should I give here? By what value should I AND with accumulator so that I can mask only the 5th bit? Okay, so think on it and try to get the answer and put that in a comment box. And if you got an answer, you put it in a comment box. If you have a doubt, you just put that in comment box. I will come with a solution for that. Okay, now I hope AND logic is clear for you. Now let us go for the another one, that is OR logic. So in OR logic, we generally make use of this OR logic to add the numbers. So we know that OR logic is nothing but what? A and B, that is the two inputs. It will give output in the similar way of addition. So 0 0 0 1 1 0 1 1. When we OR 0 and 0, 0 or 0 is 0. 0 or 1 is 1 1 1. So this is the output. Now this is going to perform like a addition. So if you want to add numbers, or you can OR it or add it, one of the same. But there is a slight difference. If both are same, there is not necessary to have two instructions together in a microcontroller. So the difference between the add and OR is, when you are executing this add instruction, there is a chance of affecting the carry. There is a chance of generating of a carry. But when you go for an OR instruction, no carry will not be generated. 1 plus 1 means you get the result. For example, when you add 1 plus 1, you get it like this, 0 and 1 as carry. This is about add instruction. But when you OR 1 and 1 or 1, when you do 1 or 1, you get result as 1, you won't get carry. So that is the difference we have between the OR and an add instruction. As I already told in the beginning of this video, I told you that these logical instructions will not affect a carry flag or auxiliary carry flag. So there is no chance of affecting any PSW flags. Okay, so if you are not bothered about a carry, then you can just make use of an OR instruction. ORL. So again you can write it like this. ORL accumulator with some number 0 to H. So whatever the content we have in accumulator, that will be OR with 0 to. Nothing but it is adding with 2, but without affecting carry, without generating carry. That is the function of OR logic. Now similarly we will have for an XOR, and we have some importance regarding XOR gate. We make use of that in a special way. So let us say that there are two inputs. Okay. So there are two inputs we have. This is what the output is. If you want to cross check, you can do it like this: A bar B plus A B bar. If I give both input as same, 0 0, Now this is 1, this is 0, plus this is 0, this is 1. So 1 into 0, 0 plus 0, the answer will be 0. So this is what how we can cross check and write a truth table. Now here, if both inputs are same, then the output is 0. That's the concept we have in XOR gate. Okay? If both the inputs are 0, output is 0. If both the inputs are high, output is 0. So if the inputs are similar inputs we have, then the output will be 0. So now I make use of this in microcontroller. So let's see how we can make use of this and for what purpose we can use it. Very simple. If you want to compare two numbers, two inputs, and if you want to see whether they are same or not, we have, for comparing, we have a special instruction called CJNE, but that is going to perform some other concepts also, and it takes more machine cycles. So instead of that, you can go for XOR logic instruction. So now I'll give an example. I'll take one input in accumulator and the other input in another register, and I see that whether those inputs are same or not. So you can, I will construct the question like this. Write a program to check the content of accumulator and register 1. If they are same, then send yes to port 1. If they are not same, then send no to port 1. This is the question. So you just need to check two data. If they are same, send yes to port 1. Yes or Y. You can just send Y to port 1. If they are not equal, then send no to port 1. This is the question. So for that, let us write a program. First, let us take inputs in accumulator and register 1. Say, I will take move R1, some input I will give, 39H. One number I have given it, and then I will take another input for accumulator, move A, like 37H. Or let me take the same number here and tell you what's going to happen in XOR gate, 39H. Okay. Now what I do, I write XRL A, R1. A, R1. Now the content of A and content of R1 will be compared together. Now what do we have in A? 39. What do we have in R1? Same 39. So 39 means 0, 0, 1, 1, 1, 0, 0, 1. This is 39, and that both registers are having the same number, and we are XORing it. So what happens? You just check it here. When you have same inputs, what is output? It is 0. So 1 XOR 1 is 0. These are all same input, same input. If you have same input, output will be 0. That's it. So all are same. So what you can see here, this will be stored in accumulator. In accumulator, what I got? 0, 0. So we can understand here that if after XOR logic application, when I XOR the data, when I execute this line, if the accumulator is 0, then you can say the content of both the registers are same. That is how we can conclude. So this is how I am going to make use of an XOR logic. I can make use to conclude that whether the inputs are same or not. If they are not same, you won't get it as 0, 0. You will get something else. Okay. So according to this, now both are same. The accumulator will get 0. The question is to check whether they are 0 or not. If they are 0, then send yes to port 1. If they are not, send no to port 1. That's the question. So now you have to check for accumulator whether it is 0 or not. Now we have a special instruction for that. JZ. Jump if 0 or jump if not 0. You can use that. So I'll check for jump if 0. When I write JZ, it will check accumulator and whether it is 0 or not. Now it is 0. So if it is 0, let me jump next. So I write it here next. So what has to be done if it is 0? According to question, it is clear that if it is 0, means if those two numbers are same, just type yes in port 1. Send yes to port 1. What I do, I write move port 1 Y. This is how we can write it. Instead of writing yes, we can write Y. So I'll send Y to port 1. This is what they have asked you to do. Now this is going to execute only if these two numbers are same. Then only we will get accumulator as 0 and this will be executed. If there is a 0 in accumulator, jump to 0, it will come here. If it is not 0, what has to be done? You have to send no, N to port 1. So if it is not 0, it will come for the next line. So next immediately what I will do, move port 1 N. So I send that N, but no to port 1. So after that again it will come for the very next line. Next line I should not execute this. If you execute it, if I say that there is not equal, if it is no, you should not execute this line. Okay. So I have to skip this. So what I do, I write sjump, some label down. I can write down here. Whereas again I can write sjump down and end the program. End the program here. So we will stop the program here. Means we are getting yes into port 1 if both the inputs are equal. If both the inputs are equal, accumulator will get 0, and I am checking for that whether accumulator is 0 or not. If it is 0, I will send it. We will jump here and it will send y to port 1. If it is not 0, then it will send n to port 1 and s jump down, short jump down. It will come here and it will end. So this is how XOR L instruction can be utilized. This is one example I am giving you in the microcontroller. Okay. So now we end up with the last instruction, that is NOT gate, that is complement. So let us see how to utilize that in microcontroller. With one example, I will explain the concept. So for NOT gate, you know that we have only one input and one output. So one input, so the combination will be 2, 0 or 1. And output will be opposite to that. That is, if it is 0, it is going to be 1. If it is 1, it is going to be 0. That's it. So the instruction used for this is CPL and operand is A, complement A. So in most of the cases in microcontroller, we need to get 2's complement, 1's complement, then we can make use of this line. So I just need to complement. If I say you want to toggle, if you want to write toggle some data, means I take a question like this. Write a program to toggle the content of accumulator for 5 times. So write a program to toggle the content of accumulator for 5 times. Okay. So whatever the content we have in accumulator, say 55H is the content in accumulator, you want to toggle it. Toggle in the sense you have to just complement it. So you can make it of a complement instruction, but you have to do it for 5 times. So what I do, first I will take some input to accumulator. So move A, you write whatever the input you want, because in the question they are not mentioned what is the input. You just give the input to accumulator and then 5 times you have to repeat it. So you do that 5 times to some register, find number to one register R1 hash 05H. Give it to register R1 and then you just write what you want to do. You want to complement it, you need to toggle it, right? So I will write CPLA. So 55 is nothing but what? 0101, 0101. So once you execute this line, it will complement all the bits of it. So what happens? This is going to become 10101010. It means this is A, this is A. So 55 will become AA. That is just a toggling of the content of accumulator. Okay, once it is complemented. Means once it is toggled. Now we can repeat it for 5 times. So what happens? I have assigned that count to R1. Now I will decrement this count. And check if it is not 0, I repeat this instruction unless and until this becomes 0. So for that we have a special instruction DJNZ. Decrement the register which is assigned for count, that is R1. Decrement R1 and jump if not 0. If this is not 0, you have to jump. So where you have to jump now? What is our task? Our task is to complement it. Our task is to toggle it. That's it. So I will jump to this line. So here you need to write some label like up, and you mention that label here, up. So it will decrement R1, R1 will become 4, it's not 0, it will come here and complement it again. So this will repeat 5 times because after 5 counts, this R1 is going to become 0 and this condition become true. Decrement and jump if not 0, but now it becomes 0. If it is 0, it will come out of the loop. And our task is done. We have complemented that accumulator for 5 times. Then I will stop the program by writing a short jump, some label, and I put it in a label here, endless label, and end. So this is how a program can be written using the instructions, logical instructions. So this is one example I have taken. You can use this complement for any kind of an application. I hope you got an idea about logical instructions and how to make use of those logical instructions in a microcontroller and how to write programs using it. If it is clear for you, you just mention it about it in a comment box, and you also can mention what is your expectation from my side. Means next what kind of a video you need to get in microcontroller. You can put it in a comment box there. And also don't forget, I have given one question. You try to solve it. If you got the answer, put it in comment box. If you didn't got the answer, also put it in comment box that you didn't got it, so that I will explain it. Okay. So thank you. This is what we have for this today's video. Thank you. and don't forget to subscribe to my channel. Thank you.